Welcome to Practice Exam 1 video. So let's go ahead and start off here. In the first question, we're looking at one-to-one functions and inverses. So we first want to state the definition that f is one-to-one. So remember that all one-to-one functions have inverses. So one way to state that definition is if you have two inputs, x and y, and they are not equal, then that implies that the outputs f of x and f of y are also not equal. So if you start with different inputs, you get different outputs. Now an equivalent way to write that is that using the contrapositive, if f of x equals f of y, so if you start with two outputs that are equal, then that implies that the inputs that you started with, the x and y, have to be equal. So either one of those is fine as the definition. So now there's some other things I could ask you to do here rather than just state a definition. I could ask you to actually show that something is one-to-one, or I could ask you other questions related to inverses there. So these are representative questions. Part B, we are given f of x is x over x plus 1. We want to find f inverse. So remember there's two steps here. What we want to do is first plug in y for f of x. So we got y equals x over x plus 1. And then what you want to do is switch your x and y and then solve for y. So where there's a y, we're going to put x, and where there's an x, we put y. So x equals y over y plus 1. And then we want to solve that for y. So let's see here. I think we want to multiply both sides by y plus 1 here to start off. So on the right and on the left. On the right hand side they cancel out. On the left hand side we're going to multiply that x in times each piece there. So we get yx, I'm going to write that as xy, and then x times 1 is x. And then on the right hand side, the y plus 1's canceled out, so we just got a y left. Now we want to solve for y, so we want to get the y terms on the left and the x terms on the right. So this is a y term and this is a y term. So we want to subtract y on both sides. We'll bring that over to the left-hand side. And I'm going to line these up. These are y terms. So these guys cancel. We get a 0. And we've got xy minus x. And, xy minus y. And then plus x. So then we also want to bring the x terms over on the right hand side. So let's subtract x on both sides. And there's really a 0 here. So that leaves us with a minus x. So we've got xy minus y equals negative x. So now we notice we've got a common factor of y here. So we've got our y terms on the left, x terms on the right. So let's factor out that common y. So if you factor that y out, this x is left here. And factor a y out of here and there'll be a negative 1 that's left. So x times y times x minus 1 is equal to negative x. And now we can divide off that x minus 1. So now these guys cancel. And we've got left now y equals negative x over x minus 1. And an equivalent way to write that, if we multiply the top and the bottom by negative 1, is negative x times negative 1 on top is x. Negative 1 multiplied by x is going to be a negative x, and the negative 1 multiplied by negative 1 is a positive 1. So it's going to change both signs on the bottom. So we get 1 minus x. So x over 1 minus x. And that's our f inverse. So f inverse of x is equal to x over 1 minus x. And that one's all set. So next up here, we want to find the derivative of the inverse at a point. So here we want to find f inverse prime at -1 if our f of x is x cubed plus x minus 1. So we're assuming that there's an implied inverse function, at least locally around -1. And remember that this -1 is not an x value, that is a y value, because x values are inputs for the function and y values are inputs for the inverse function and then also its derivatives. So what we don't want to do is try and solve this equation for x, switch x and y and solve for x. We don't want to do that because it's actually not possible. What we want to do is we want to use this formula for the derivative of the inverse at a point, and that's f inverse, that should be a prime, f inverse prime at a value y is going to be 1 over f prime at f inverse of y. Okay, so this f inverse of y on the inside, that's an x value. Okay, inputs for f inverse are y's and then outputs are x's. So we want to find this at -1. Okay, so we want to do 1 over f prime f inverse at -1. So we want to find the value of this guy right here, f inverse of -1. So what is the x value that goes with y is -1? Okay, well, f of x and y are the same. So what we do is we take y equals x cubed plus x minus 1, and we're going to plug that y equals -1 in here for our f of x. So you take your x cubed plus x minus 1 and set that equal to -1. And then you should be able to just look at this equation and by inspection find a solution, easy solution like 0, 1, -1, something like that. Notice that x equals 0 is a solution of this. So x equals 0 is one solution. Sometimes there's more than one. And actually, I think -1 is also a solution here, because that would give -1 cubed is -1, and let's see, plus -1. No, my mistake. If this was a square, if this was a square, then -1 would be a solution. But sometimes there's more than one solution. You just need one. So this inside here, that's 0. So this is now going to be 1 over f prime at 0. So now this is the regular derivative at 0, and if our f of x is x cubed plus x minus 1, then our derivative function, just use power rule, polynomial, is going to be 3x squared plus 1. And now we just got to plug in 0. So this is just going to be 1 over 3 times 0 squared plus 1, which is just 1 over 1, which is 1. Okay, and that's our final answer there. Okay, so the key, there's two steps here. We've got to find this f inverse of y. We've got to find the x value that goes with this given y value. And then the second is to plug that into 1 over f prime. In the next problem, they want us to simplify the cotangent of inverse cosine of 2x. So this problem is just kind of working with the definitions of the trig functions and their inverses. So remember that the inputs for inverse functions are the values of the trig functions, and the outputs are angles. So this this quantity here, inverse cosine of 2x, that is actually an angle, and let's call that theta, because you're going to take cotangent of it. So cotangent of this angle is what we're looking at. We want to try and simplify that expression. So if theta is going to be equal to our inverse cosine of 2x, and remember the way that you can read this is the inverse cosine is read as the angle whose cosine is. So the angle whose cosine is 2x, that's theta. So this translates into Well, if you take the cosine of theta, you get 2x. Okay, that's what inverse cosine 2x equals theta means. And then cosine of an angle, remember, is adjacent over hypotenuse if you're looking at right triangle trig. So we'll just write this as 2x over 1. And now let's go ahead and we'll draw a right triangle that fits for this problem. So here's our angle theta. And cosine is going to be, this is adjacent over hypotenuse. So the adjacent side is going to be that 2x. And then the hypotenuse on this triangle is going to be 1. This is right triangle. And then remember, this side that's left is going to be hypotenuse squared minus leg squared square root. So this is going to be 1 squared, which is 1, minus the 2x quantity squared, and then square root, which is the same thing as 1 minus square the 2, you get 4, and square the x, you get x squared. So root 1 minus 4x squared. Okay, so now we've got our triangle all filled in, and what we want to do is we want to know what is the cotangent of that angle theta. Okay, well, cotangent of theta, right triangle trig definitions, tangent's opposite over adjacent, cotangent is adjacent over opposite. So adjacent to this angle is the 2x, that goes on top, and then opposite of the angle is the root 1 minus 4x squared, and that guy goes on bottom. And of course there's going to be domain restrictions here for which this makes sense, because root 1 minus 4x squared is not always positive, but that's okay. We've simplified the expression. We're not requiring the domain restrictions to be stated here. Next up, we have some derivatives to do here. So we want to find y prime from the following functions. First, y is inverse sinh of 2x times the log base 5 of x cubed. So notice first that this is a product, so it's going to involve a product rule. Let's let the function sinh of 2x be our f, and let's let the function log base 5 of x cubed be our g. Then our y prime here is going to be equal to, we'll write the formula underneath, f prime times g plus f times g prime. And we're not simplifying, and it'll be that way on the exam too. So remember that the derivative of sinh is cosh. So derivative of sinh 2x is going to be cosh 2x. Okay, but since we're doing cosh of a function 2x, you have to multiply by the derivative of the inside function. So that'll be times 2. And then we'll multiply that by our g of x, which is going to be log base 5 of x cubed. And then plus our f is just sinh of 2x. And then g prime, the derivative of a log of a function. Remember, if you've got natural log of a function f of x, and actually I think we used g of x, that the derivative of this, the prime of that, is function on the bottom, so it's 1 over g of x, times the derivative of that inside function, g prime, so we get g prime of x over g of x. And then if it's log with a different base, then remember what you need to do then is you need to divide by the log of the base. So if you're doing log base b of a function g of x, and you want to do the derivative of that, it's still going to be g prime of x over g of x. But then on the bottom you need log of the base. So natural log of b. And that's what we need to do to find this g prime, the derivative of this. So our inside function is x cubed, so that is going to go on the bottom. And then its derivative is 3x squared, that goes on the top. So derivative of the inside over the inside. And then the base is 5, so we need to add that correction factor on the bottom times the log of the base, ln 5. And that's good enough, just like that. In the second one here, we're finding the derivative of log of a function. So this is this log of this whole function, root of x e to the x over hyperbolic tangent of x. And, you know, we could use this formula again, but if we do, it's going to get kind of messy when we do the derivative of the inside, because we've got this, you know, this is going to be power rule for functions and then also a quotient rule involved in there. So it's going to get a little crazy. So what we want to do is try and simplify this using properties of logs as much as we can first. So this is division inside, which is subtraction outside. So do log of the top, root x e to the x, minus log of the bottom. So natural log of that hyperbolic tangent. And then remember that a square root is a 1/2 power, and inside exponents for logs factor down. So this is going to be natural log of this x e to the x, and that gets a 1/2 power on it. And then minus the log of that hyperbolic tangent. And then remember, this guy will come down in front. So now we're still just simplifying here. So this is 1/2 natural log of x e to the x. And then minus natural log of hyperbolic tangent. Okay, so now here we've got multiplication inside the log, and remember, multiplication inside is addition outside. So we can write this as 1/2 times the natural log of x plus the natural log of e to the x. And then minus natural log of that hyperbolic tangent on the end. So I haven't done anything else with him. And then the natural log of e to the x, ln and e, those are inverses. They undo each other. So they cancel each other out. This is just an x. So this is now going to be, I'm going to go ahead and distribute the 1/2 in the same step if you'll let me. So 1/2 times ln x, so it'd be 1/2 ln x. And then this is x, right? The x is left, log and e cancel out, times 1/2, so plus 1/2 x. And then we got that minus ln hyperbolic tan still down on the end there. And now it's simplified. So simplify as much as you can first with logarithms, and then take your derivative. So this is all still equal to, this is all equal to our y that we started with. So then what is y prime? We'll just differentiate term by term. So the derivative of log x is 1 over x. This is going to be 1/2 times 1 over x. And derivative of 1/2 x is just 1/2, so plus 1/2. And then minus, now this is derivative of log of a function, so natural log, and so that's this formula, g prime over g. So the inside goes on the bottom, hyperbolic tangent downstairs, and then derivative hyperbolic tangent is hyperbolic secant squared on the top. And again, no simplifying, we can just leave it like that. We're good. And then our last derivative here is inverse sine of 3 to the 2x power. So this is inverse sine of a function, so we are going to have to use the chain rule here. Okay, so this looks like an f of g of x. Okay, and remember that when we do our y prime here, the derivative of f of g of x, you've got your f of g of x, that composition, and if you take the derivative of that, the prime of that, you get the derivative of the outside function, f prime, at the inside function, g of x, and then times the derivative of the inside, g prime of x. So that was one way that we wrote our chain rule. Okay, so what's our outside function? Well, that's inverse sine. So remember that the derivative of inverse sine is 1 over root 1 minus x squared. So inverse sine of x prime is 1 over root 1 minus x squared. So we're going to do that same thing. We're going to do 1 over root 1 minus, but not x squared, parentheses squared. And what goes inside those parentheses? Well, our function g of x, our inside function, which is that 3 to the 2x. So that goes in here, 3 to the 2x squared. And then times g prime of x, that's the derivative of our inside function. So let me write an extra step here. So times the derivative with respect to x of 3 to the 2x power. Okay, so now all we have to do is simplify that derivative and we're set. So the first part stays the same, 1 over root 1 minus 3 to the 2x power squared. Now notice you could simplify that if you wanted to. It's a power to a power, you can multiply, but we're not requiring simplification, so we'll just leave it. And then remember, if you differentiate an exponential, this is an exponential to a function power. So if you differentiate, let's see, let me write that formula up here. If you start with a base b and you've got a function power, so let's see, let's call it f of x. So remember, if you differentiate e to a function, you get e to the function back times the derivative of the inside function. Well, if we differentiate another base to a function power, we'll get that base to the function power again, and then times the derivative of the inside function, so times f prime of x, and then you got that correction factor. Since it's not e, you have to do times log of the base. So ln of, that doesn't look like an n, ln of the base. So this is what we want to do for this derivative. So we're going to get 3 to the 2x, okay, that's this part, and then times the derivative of the inside function, which is a 2, and then times the log of the base, natural log of 3. Okay, and then we could, again, we could do some other simplifying, but we're not required to do that. So that one's all set. So next up, we are looking at some integrals here. So before we start on these integrals, why don't we take a look at the formula sheet here, the study guide, and notice some of the patterns here, or recall some of the patterns. So with our inverse trig functions here, if we've got an integral that looks like square root of a square, one's a perfect square, so a number squared minus a quantity in terms of x squared, that's going to be inverse sine. If there's no root on the bottom and there's a sum, then that's going to be an inverse tangent. And then down here with the inverse hyperbolics, if we are integrating something that looks like 1 over the square root of a number squared plus an expression squared, that's inverse sinh. If they're switched and it's an expression in x squared minus a number squared, then it's inverse cosh. And if there's no square root on the bottom but it's a minus sign in between them, number squared minus an expression in x squared, inverse hyperbolic tangent. So we want to notice those general patterns first. Oh, and then of course the general pattern for log functions. Let's see here. Remember, integral of 1 over x is natural log absolute x, and then integral of g prime over g is natural log of absolute value of g of x. So let's go back to our problem here. So I look at this one and I see that x to the 8th power on the bottom, and I see the x to the 7th on the top. And if you differentiate x to the 8th, you're going to get an x to the 7th. So I'm thinking this looks like g prime over g. So let's try and do a u substitution here and simplify it. So let's let u equal x to the 8th minus 4 on the bottom. Then your du is going to be 8x to the 7th. Derivative of negative 4 is 0, and then we need a times a dx. Well, up on the top, we've got a 3x to the 7th dx. So let's take this 3 and we'll bring it on the outside here. So we'll have a 3 on the outside. Integral of, on the top we've got left x to the 7th and a dx. And then downstairs we've got that x to the 8th minus 4. So now we want to have 8x to the 7th, so let's multiply by 8, and then we'll divide by 8 on the outside to compensate. So that maintains equality. And now we've got our du here, and our u on the bottom. So with a little bit of algebra, that is 3/8. And now we're integrating du over u, or 1 over u du. Okay, so that's just going to be natural log of absolute u, okay, from our study guide, and then plus a constant. And then don't forget to change back to x's. So now we just have to plug back in our u substitution there, x to the 8th minus 4. So natural log absolute x to the 8th minus 4, and then plus c. Don't forget your constant of integration. And we do need the absolute values here because even though the x to the 8th is always positive, if x was 0, 0 minus 4 would be negative. And remember, you can't take the log of a negative. So we do need those absolute values. In part B here, I look at this, I see that square root on the bottom, I see an expression in x that's a perfect square, and then I see that 36, which is a perfect square. So I'm looking at that, so expression squared, square root, expression squared minus number squared. So if we go back to the study guide, look at our formulas here. So square root, here the number squared minus the expression, and then down here it's the expression minus the number. Okay, that's what we've got there. Okay, so it looks like that's an inverse cosh. So let's go ahead and bring that formula over. Miniaturized. Let's pump it up a little bit there. Okay, so that's what this guy looks like, except this has got a 1 and here we've got a 36. So we've got to do a little bit of algebra here to get it in the right form. Might have to do a u substitution here because this is x squared and this is x to the 12th, so that's not just x squared. So but the first thing we need to do is we need to have a 1 right there instead of a 36. So what we want to do here is we'll leave our 2x to the 5th on the top for the instant. And then down in the denominator, we want to factor out that 36 on the inside here first. So if you factor out a 36, if you factor it out of here, you're just going to have a 1 left, well, negative 1. And if you factor it out of here, you have to have a 1 over 36 times x to the 12th. So if essentially you divide by 36 when you factor that 36 out. So now if you multiply this back in times each piece, you still get your x to the 12th minus 36. So now dx out on the end, and now we can take the square root of each piece on the bottom. So we can break off that square root of 36, which is a 6 in the denominator. So this is now going to be integral 2x to the 5th. And then square root of 36, see in the denominator we're doing this, root 36, and then root 1/36 x to the 12th minus 1. Because remember, square roots of products and quotients you can break apart. So root 36 in the denominator, that's a 6, and then this part we have to leave. But notice what we want to do is we want to have an expression squared minus 1. Okay, so you want to write this as a square. Well, 1/6 is what you square to get 1/36, and x to the 6th is what you square to get x to the 12th. So that is really x to the 6th divided by 6 quantity squared. Or if you want, it's 1/6 x to the 6th squared, and then minus 1 dx. So now this guy looks like this expression. Okay, so now let's go ahead and do a u substitution here. Well, actually, we can do a little bit of simplifying here. 2 goes into 6 3 times there. And now let's go ahead and do a u substitution. Let's let u equal this guy here on the inside. U is going to be x to the 6th divided by 6, or 1/6 x to the 6th. And let me go ahead and take this guy out of here. Get myself some room. Okay, so let's see here. U then is going to be equal to, I'll go ahead and write it as 1/6 x to the 6th, because then our du is going to be 6 times 1/6 is 1, and then decrease your exponent, x to the 5th dx. So, well, we've got an x to the 5th dx right here. There's our du. So we're all set there. So let's take this 3 that's in the denominator and let's factor that out. So that's really a 1/3 on the outside because the 3's in the denominator. And then integral, what do we got left? Du on the top. And then on the bottom, this is going to be u squared minus 1 square root. Okay, now it matches this pattern. The derivative of inverse cosh is 1 over root x squared minus 1. So if you integrate this, you get back to inverse cosh. That's actually not the formula I wanted to bring over. I wanted to bring over the integral version of that. Let's do that. Let's go back here. So this is the derivative version of that, and this is the integral version. I want the integral version. So if you integrate that, root x squared minus 1 in the denominator, then you're going to get back your inverse cosh. So what we were doing is we were making the integral that we had look like this left-hand side. So you're matching a pattern. There we go. So now this looks like the left-hand side. We bring that 1/3 along for the right. Don't forget your constant. And this is now going to be inverse cosh, not of x, but of u. So inverse cosh of u, that's a -1. And then plus constant, because it's an indefinite integral. And then we got to go back to x's to finish up here. So this is just going to be, move this guy up. Got a 1/3 on the outside, and this will be now inverse cosh, and our u is the 1/6 x to the 6th, and then plus a constant, and we got it. So we're just matching those patterns. So the last integral here, now notice we've got a quantity squared. I see that x squared, and then 1's a perfect squares, and we've got a plus in between them. So we go back to our study guide here and see which pattern that matches. So no square roots, it's going to be either this one here or it's going to be this one here. Well, this one's got a minus and this one's got a plus. So it's got to be the inverse tangent. So let's go ahead and grab that formula and bring it over. So we want to make this guy match this formula. So we've got the 1 right here, so we want to write this as a perfect square. We're going to have to do a u substitution on that one too. So let's see here. So it's going to be integral from 0 to 1/2, definite integral on this one. So we're going to get a numerical answer. We've got that 2 up on top. On the bottom, 4x squared, square root of 4 is 2, square root of x squared is x. So that's 2x parentheses squared plus 1. And so that 2x, that's going to be our u. So here u, need a dx on there. So u is going to equal 2x. And so our du is going to be 2 times dx. And oh, looky here. Well, that worked out nice. There's our du. So now we want to change the whole integral over to u. So this is going to be integral. We've just got du on the top. And then downstairs we've got, this is now going to be u squared plus 1. And then these are x values. We need to change those over to u values also. So your limits of integration have to be in u. So if x is equal to 0, then plug that into the u equation. Then u is going to equal 2 times 0, which is 0. So this is going to be still 0. If x is equal to, on the top here, 1/2, then your u is going to be 2 times 1/2, which is equal to 1 there. And then the antiderivative of the u squared plus 1 is going to be inverse tan of u. So this is going to be inverse tan of u. And it's a definite integral, so we don't have a plus c, but that's going to get evaluated from 0 to 1. So plug in 1, plug in 0, and subtract. So this is going to be inverse tan, plug in 1, minus inverse tan, and plug in 0. So this is the angle whose tangent is 1, and it's got to be between negative pi over 2 and pi over 2. That's the domain of inverse tan. And that angle is pi over 4. If you pull out your unit circle, you'll see that, remember, pi over 4 has the same sine and cosine, so that makes the tangent equal to 1. And then the angle whose tangent is 0 is equal to 0. So this is just pi over 4. So we do want an exact answer there if you can evaluate these things. And we can. Okay, and in our next question, looks like we are doing some logarithmic differentiation here. So we want to differentiate this complicated expression using logarithmic differentiation. So remember, logarithmic differentiation you'll use for these, complicated quotients and products to powers, but you'll also use logarithmic differentiation if you've got a function base and then a function power, and you're taking the derivative of that. Okay, so that's another thing that you're going to use logarithmic differentiation for, is something that looks like that. And remember, this one, what you have to do is set the expression equal to y, and then you have to take logs on both sides. Okay, and that's what we're going to do here. So let's see, we start out here by setting y equal to this e to the x cubed times cosine 12th of x, and then divide by x plus 5 to the 50th. So if we were going to do this without logarithmic differentiation, we'd have to use a quotient rule and then a product rule in here, and then for finding the individual pieces, we'd have power rule for functions, and it'd be a total mess. So remember, what we want to do here is we want to take logs on both sides. So the natural log of y is going to equal the natural log of this expression here. Let me just copy that guy and bring it over. And then remember, what you want to do is you want to use properties of logs to simplify this as much as possible before you differentiate. So we've got a division here inside the log. So division inside is subtraction outside. So it's going to be log of the top, which is that e to the x cubed, cosine 12x, and minus log of the bottom. So it'll be ln of the x plus 5 to the 50th. And then let's see, in the next step, exponents, inside exponents will factor down. That 50 can come down. And then this is a multiplication inside. So multiplication inside is addition outside. So we can break this apart as the natural log of e to the x cubed plus the natural log of the cosine 12th of x and then minus 50 ln of x plus 5. And now let's see, on this first piece, natural log and e are inverses. They cancel each other. We're just left with an x cubed plus, and then here that 12 can come down in front. That's an inside exponent because this means cosine x whole thing to the 12th power. So that's going to be 12 natural log cosine of x. That's log of a function. And then minus the 50 ln x plus 5 on the end. Okay, so we simplified as far as we could. So now we'll go ahead and do our derivative. Okay, so now our y prime here, I'm sorry, our derivative on the left, the derivative of log y. Remember, if you take natural log of y and you do the derivative of that, this is log of a function, y is a function. So instead of g prime of x over g of x, remember if we go back to our formula sheet here, let's see, where are we here? They're right there. Log of a function is function on the bottom, derivative on the top, g prime over g. So that's what we're doing here. So y is a function, so the function goes on the bottom, its derivative on the top, y prime over y. So the derivative of this left-hand side is y prime over y. And then the derivative of this right-hand side here, well, derivative x cubed is just 3x squared plus 12. And now this is derivative log of a function. So again, we got to do this again. Inside goes on the bottom, cosine x, and derivative on the top. Derivative of cosine is negative sine. And then minus 50. And then this is a function again. So function goes on the bottom, x plus 5. And derivative on the top, derivative of x plus 5 is 1. And now we want to solve for y prime. So multiply both sides by y. And these y's all cancel. And there we get our y prime is equal to this whole thing. And I'll do a little bit of simplifying in there. Let me scooch this guy over. 3x squared. And then let's take this minus sign and we'll bring it out in front. So minus 12. And you could leave that as sine x over cosine x, but remember sine over cosine is tangent. So let's go ahead and change that to tan x. And then 50 times 1 over x plus 5 is 50 over x plus 5. So that's our inside the parentheses simplified. Then we multiply by y. Y is that original function. It's an original expression there. Okay, so which is this guy here. Okay, so that's going to go up here on the end. So actually, let me see. I guess I really don't quite have room. Let's move that guy down there. So there we go. Okay, so then our y prime is, this is the inside right here simplified, and that y is this guy right here. So a lot of work, but you know what? If you did it without logarithmic, it would be way more work. It's like a detention problem. You get caught texting in class. You have to do a problem like this longhand. Okay, it looks like we got some limits here to look at. So this first limit, we're looking at limit as x goes to infinity, e to the 4x plus e to the negative 4x. Over e to the 2x minus e to the negative 2x. So let's look and see. Remember, x is going to infinity, so this exponential is going to a big positive exponent. It looks like e to the infinity, which goes to infinity. And then this one looks like e to the minus infinity, which goes to 0. Remember that your exponential function looks like this, with a positive exponent, that's e to the x. And so as you go out to positive infinity, it goes up to infinity, but as you go out to minus infinity, it comes down to 0. So this looks like infinity plus 0 over, this one's going to go to infinity, and then negative exponent, that one's going to go to 0. This is form infinity over infinity. So we could use L'Hopital's rule on that one. Or, a little bit less work. Actually, if you use L'Hopital's rule on this one, I think you kind of go around in circles because you differentiate e to the 4x and you just get e to the 4x back again, and nothing ever disappears. So actually what we want to do on this one is we want to do multiplication on the top and bottom. And what we want to do is have negative exponents everywhere we can get them. So this is going to be equal to limit x goes to infinity, e to the 4x plus e to the negative 4x over e to the 2x and minus e to the negative 2x. And what we do is we look at that biggest positive exponent, which is a 4x, and we multiply by e to the negative 4x. Because remember, when you multiply, you add exponents, so we want the thing that's going to make this add to 0, which is going to be a negative 4x. We multiply on the top and the bottom, that way we're not changing the value of the expression. So now this e to the negative 4x comes in times each piece here, and same thing on the bottom. Remember, when you multiply, you add exponents, so 4x and a negative 4x is just 0. So we're still taking a limit here as x goes to infinity. And then this will just be e to the 0, which is 1. And then e to the negative 4x times e to the negative 4x, you add the two exponents. So negative 4x and negative 4x is going to be negative 8x. So plus e to the negative 8x. And then down on the bottom, e to the negative 4x times e to the 2x. 2x plus negative 4x is going to be e to the negative 2x. And then minus, that's this minus sign. Multiply these two guys, you add your exponents. Negative 2x and negative 4x is negative 6x. And now, the top, this piece is approaching 0. So this approaches 0. This piece here, as x goes to infinity, that's e to a big negative exponent. That approaches 0. And then this one also approaches 0 because they're negative exponents. But then we've got a 1. So this now looks like 1 divided by 0. Okay? And a number divided by 0 is going to go to either plus or minus infinity. So remember, if you've got something form number over 0, that always gives you plus or minus infinity. You have to determine the signs at the top and the bottom. Well, e to a negative exponent, doesn't matter whether it's positive or negative, e to an exponent is always going to be positive, right? This comes down, it's asymptotic to the x-axis, but doesn't cross over. So positive number plus a positive, this is positive on top. And then on the bottom, e to the negative 2x and e to the negative 6x, this is a bigger negative exponent. That's going to be a smaller number. So this difference here is actually going to be positive also. So this is positive divided by positive. This is going to be plus infinity. And if you have trouble seeing that, you can always plug in a number, like, plug in 1,000 on the bottom and see if it's positive or negative. And you can do the same thing on the top. As long as you know it's form number over 0, because you know number over 0 is either going to be plus infinity or minus infinity. Okay, next up, we are looking at limit as t goes to infinity, 3t squared, e to the minus 4t. So let's see, as t goes to infinity, this piece here approaches infinity. And then e to a big negative exponent, as t goes to infinity, negative 4t goes to minus infinity. So e to a big negative exponent, that's going this direction. That's going to approach 0. So that's form infinity times 0. So remember, we want to change that around so it's either 0 over 0 or infinity over infinity. So why don't we see this e with a negative exponent, why don't we bring that down to the bottom with a positive exponent? We can rewrite this as limit as t goes to infinity. And we'll leave that 3t squared up on top. And e to the negative 4t on the top is e to the positive 4t on the bottom. And now as t goes to infinity, the top is approaching infinity, the bottom's infinity. This is infinity over infinity. That is now an indeterminate form, so we can use Mr. L'Hopital's rule on there. We'll put an L up there to let us know we're using L'Hopital. And you differentiate top and bottom separate, remember? Not quotient rule. Don't do the quotient rule here. It's L'Hopital. So derivative 3t squared, that's going to be 6t. 2 times 3 and decrease your exponent. Derivative e to the 4t is going to be e to the 4t, and then times the derivative of the inside, which is 4. So it gives you an extra factor of 4. And t is going to infinity. 6t approaches infinity. 4e to the 4t approaches infinity. That's still infinity over infinity. It's still indeterminate. So we can do L'Hopital again. Don't forget your limit sign, because the two limits are equal, but the expressions aren't equal. So this equals the limit as t goes to infinity. Differentiate 6t, and now you got a 6. And differentiate e to the 4t, you get e to the 4t times 4 times another 4 out in front. That's 16 e to the 4t. And now the top is a number, 6, and the bottom is approaching infinity. So number over infinity, that's going to 0. Top is fixed, bottom's getting bigger and bigger. So this limit is 0. So, and then just remember your limit signs in here. So these two limits here, those are equal. Okay, the limits are equal. But if I take those limit signs out of there, okay, if I take the limit signs off, okay, then those are no longer equal to each other, right? 3t squared over e to the 4t, that is not equal to 6t over 4e to the 4t. Their limits are equal, but the expressions are not. Okay, so don't forget your limit signs when you do L'Hopital's rule. Alrighty, and one more question here. And by the way, this practice exam, this one is longer than the actual in-class exam, just in case you're wondering. So I gave you more practice problems than I normally would. So it is actually a copy of an old exam, but it ended up being way too long, and I'm like, oh, I got to shorten this up a bit. So this is actually a little bit longer than you're in class. Okay, so here we're doing a limit, and we've got a function base and a function power. X is approaching 0 from the plus side. The base looks like 1 plus x, and the exponent 1 over x. So what's happening here is as x goes to 0, 1 plus x is approaching 1 plus 0, or 1. So this is form 1 is your base. And then x is approaching 0 from the plus side, so this looks like 1 over 0, which goes to infinity, and it's positive infinity because x approaches 0 from the plus means x is greater than 0. So this looks like 1 to the infinity. That's an indeterminate power. You can use L'Hopital on that. So remember what you do is you set y equal to the expression you're trying to find the limit of, 1 plus x to the 1 over x power. And then we take logs on both sides. So natural log of y is equal to natural log of this 1 plus x to the 1 over x power. And then inside exponents factor down. So simplify using properties of logs. So this is now 1 over x times the natural log of 1 plus x. And we could write that, divide this by 1. Any expression is the same as that thing divided by 1. Multiply straight across. That's just natural log of 1 plus x on top, and just x on the bottom. Okay, so that's our expression for log of y. So what we're going to do here is we're going to find the limit as x approaches 0 from the plus side of the natural log of y. So notice we're not doing the y prime over y. That's for derivatives using logarithmic differentiation. This is L'Hopital's rule, so this is different. So what we want to do, a little bit different. This part's the same, taking logs on both sides and simplifying, that much is the same. but we're going to take limits instead of derivatives. So limit as x approaches 0 from the plus. And now we've got natural log of 1 plus x over x. So I just brought this guy down. So now let's see what form this is. So as x approaches 0, this is looking like 1 plus 0 on the inside, which is 1. Log of 1 is equal to 0, so the top is 0. And x is approaching 0, so this x approaches 0. It looks like 0 over 0. We can use L'Hopital on that. So this is going to equal limit. Don't forget your limit sign, doggone it. X approaches 0 from the plus side. Take your derivative on the top. Well, this is log of a function. So remember how you differentiate that. Function goes on the bottom, 1 plus x. And the derivative of that goes on the top. Well, derivative of x plus 1 is just 1. And then the derivative of this x is 1. The derivative of the top function, derivative of this guy is right here. Derivative of x is right here. And, well, anything divided by itself is just itself. So this is just 1 over 1 plus x, and x is approaching 0. So we're just doing limit as x approaches 0 from the plus side of 1 over 1 plus x. Well, that's just 1 over 1 plus 0. You can just plug in to get that limit because it's continuous, which is 1. So that's what the log of y is approaching. So the natural log of y is approaching 1. Well, we want to know what is, this is the expression for y. We want to know what is y approaching. So you have to exponentiate on both sides. So then e to the natural log of y is going to approach e to the 1, which is e. Okay, so this limit here is going to be equal to e. So that's your final answer. So equals e. So don't forget to undo your logarithm by exponentiating. Okay, we took logs on both sides from here to here. So once we got our limit, we had to exponentiate on both sides to get our final answer. Okay, so I covered a lot of the different types of questions here, but this isn't completely comprehensive. So you want to go ahead and try and work the other practice exam with no study aids. Okay, so study the formula sheet on the study guide, and then try and take that other practice exam with no study aids, and then you're really going to know which problems you need to work on. Because it's real easy to go through the exam with a study guide sitting there, or this practice test, go through the other practice test and work until you get stuck and look over and say, oh yeah, that's what you do. I knew that. Well, no, you didn't know that because you had to look. So if you do that, you're going to fool yourself into thinking you're more prepared for the exam than you really are. So try and take the second exam with no study aids, push through, and then whatever you need help on, you need to get together with either me or a tutor at ACC or Math Lab and do some extra problems, practice problems that are like the ones that you missed. So now notice here, when I did integral derivative formulas, I did not use every possible formula, so I'm going to rotate these around. So for example, if I use inverse cosh, here I use inverse cosh on this practice exam, maybe I'll do inverse hyperbolic tangent on the actual. Or maybe I'll do inverse sine. So I couldn't. I didn't want to do so many problems that you're brain dead by the time the review's done. But I can rotate around these different formulas. So you want to make sure that you know all the formulas that are on the study guide. That's everything that you need to know for the exam. I know it's a lot, but memory's a good thing. So make yourself some flashcards or whatever you need to do there. All right, I think that's a wrap.